end.
You may know. Student. Well, for graduate students get coding. This is not a normal graduate student. He was actually a witness, never admitted to University of Illinois. So he went to the inferior state school called University of Chicago. It's the city university, not the state university. But he works on DES. He went to University of Michigan as an undergrad, went to U Chicago for grad school, worked on DES. He's defending Monday. Can't even call him doctor yet.
Yeah, you can't call me doctor yet.
And he's gonna start at Stanford as a Hubble Fellow sometime September.
Yeah.
Okay, so let's welcome Dhayaa.
Thank you. It's a very kind introduction. I appreciate it. So as Joaquin mentioned, I am heading to California in a little bit, so I very much jumped on the opportunity to come by and say hello to a couple of people before I head out. And as I discovered, Kedar was apparently on my admissions interview as well, which I didn't realize. So
I didn't put him on the win.
Yeah. That's actually what this is about. I'm here to figure out what was going on.
Yeah.
I haven't quite got
scores.
Yeah, set on some scores really. I haven't quite done it yet, but I got a couple hours left. Okay, so I'm going to tell you today this story about studying the early universe, the physics of the early universe, by using measurements that you might often see in astronomical surveys, like optical surveys that are taken with CCDs, or millimeter wave surveys like the South Pole Telescope, and so on. There'll be a little bit of a particle physics flavor to this, but I'm going to keep it very minimal. But please feel free to interrupt and ask me any questions if something is kind of glazing over and I haven't explained it as much. All right, so I'll start by telling you what I mean by primordial physics. In this case, early universe physics can mean many different things depending on what you're interested in. So what do I really mean by that specific term? What do we have to do, or what have we had to do in order to connect this physics to the measurements that we make in surveys today? There's a reason that you might not often see these two things connected, and so let me talk a little bit about what we've had to do in order to make that connection. And then finally, talk a little bit more about this world of multi-wavelength surveys that we're in. Maybe you've heard this in many talks. You have multiple people here working on this intersection explicitly. And so how do we utilize these kinds of models to take data, use data not just from one survey, but from many multiple kinds of surveys? Okay, so what do I mean by primordial physics in this regard? I mentioned primordial physics, I mentioned late time parts of the universe. So I have to show you this very classic diagram from the WMAP team. But I'm actually not going to use this, even though you've probably seen this 100 times. Even if you're not a cosmologist would have shown you one. So to keep things fresh, I'm going to show you this very poorly drawn Google Slides version instead. So this is t is equal to now, the present time of our universe. And then here, t is equal to 0 is what I'll nominally refer to as the Big Bang. Just colloquially, that's what we think of. It's formally just the earliest epoch of our universe we can meaningfully talk about. And so as you go from left to right, you're looking at the universe's size evolving over time. And there's this period at the very early epoch that's called inflation, where there's a very rapid expansion of our universe. A lot of the physics I'm talking about is going to be pertaining to that specific region. But as cosmologists, we've spent a tremendous amount of time and energy looking at the physics and the measurements that we can make in this kind of intermediate to later period. So when you hear about talks pertaining to dark matter, to dark energy, neutrinos, so on, you're normally referring to things that govern the physics of this period. So this is something I actively work on as well. As Joaquin mentioned, the Dark Energy Survey will maybe surprise you, studies dark energy. And so we spent a lot of time on these topics. But now I'm very interested in taking what we've learned, the methodologies, the way of framing questions, asking questions, but then applying it to this very early universe period instead. So it's using a lot of the techniques that we built up as a community, but reframing it for a new kind of problem, so to speak. One of the reasons this is a very interesting epoch of the universe to study is maybe best encapsulated by the energy scale that's relevant during this time. We think whatever physics happened here was occurring at about 10 to the 15 giga electron volts. So to put that in some context, the highest energies we can achieve terrestrially on a lab experiment on Earth is at the LHC at CERN, and it's about 10 to the 5 giga electron volts, so about 100 tera electron volts if you upgrade the LHC, which will happen sometime soon. And so there's a very wide gap between these two energy scales. And that's very useful to have. One way to think about it is maybe something a little bit more familiar to you, being at Illinois, is thinking about the dark matter space, where there's a very wide range of potential dark matter particles one could have. And depending on what mass range you're focusing on, there are different kinds of processes and observables you can use to probe those specific processes. And so in a similar sense, if you have a wide range of energies you can access, the kinds of particle physics you can think about also varies significantly. Yes, go ahead, Gil.
Why do you think it's happening at 10 to the 15 GeV?
I mean, this is mostly 10 to the 15 or below based on the constraints that we get from R at this point.
Right. But it could be like,
It could be way low. Yeah, that is true. That is true. You're right. You're right. It could totally be that we live in a universe where the energy scale is actually just barely above the LHC or something like that. And in which case, some of the things we work on would not be that great. We'll not actually find something. That is true. It is likely. The things that I'm talking about, I didn't want to bring it up, but you brought it up. So the things that I'm talking about here, it really just, the physics that I'm talking about only is set by the energy scale, in the sense, if this energy scale was lower, you'd be studying a different kind of particle that is governed by that energy scale. So the large set of things I'm speaking of will not really be sensitive to this specific energy scale. If you lower this, then the particle you're studying is kind of like a filter. If you lower this, it's going to be at that energy scale instead. Okay? So for now, let's take that this is the energy scale. It could be lower. Gil will tell us in a couple of years, maybe. And so a couple of years, probably?
yeah, sure.
Okay. So there are a number of concrete models you can write down. Given this energy scale, there are a number of things that you can write down for what happens. These are just a bunch of words, a bunch of names. You don't have to think about this in much detail. It's mostly just to show you, I'm not making this up. There are real models with real references. A couple of these are actually from Peter Adshead as well, though I haven't cited that here, so it's maybe good that he's not here because I messed up. But there's a number of concrete models you can look at. And normally, like I mentioned before, these are all governed under this paradigm called inflation, where the universe is expanding very rapidly at the earliest epochs. And it's governed by this particle that's called an inflaton. You don't really need to know too much about the particle physics of this, honestly, because we also don't know too much about the particle physics of this. But I'll use this term a little bit. You can just think of it as something that causes inflation, is the main idea. I'll also refer to this term primordial non-Gaussianities. It's what we think is the kind of signature that's imprinted from having these more extended models of particle physics in the early universe. So these are just nomenclature that I'll use quite often. FNL I'll define later, but it'll show up. Okay. So the main point then is, let me take some physics that is happening here, and once it's trace how it impacts the objects that I see today at t is equal to now, the galaxies that I see today. If you're not familiar with this kind of topic, this might seem a little weird to you, that why is something this early on at that high energies have anything to do with the galaxies that I see today, and star formation and structure formation and so on. An easy way to think about it is thinking about the origin of structure itself. There are manifestly structure are fluctuations in our universe, places where there's a lot of mass, and there are other places where there's no mass at all. So where does that start from? In the early universe, there's a lot of energy, either 10 to the 15, 10 to the 6, 10 to the 7, what have you. But that energy is not uniformly distributed. There are fluctuations on top of this distribution. And so here's a cartoon diagram for the overdensity and the underdensity in the energy as a function of just one Cartesian coordinate. It's a simple cartoon. And so these fluctuations in the energy will eventually become fluctuations in the matter itself. So protons, electrons, dark matter, what have you. And that will then grow to become the galaxies that we see today. So parts of the universe where there's many fluctuations maybe become a group of galaxies. If there's a single one, maybe you get a big galaxy, and so on. So if you study the statistics of this, you can back out, in some sense, the statistics of this piece. And so why is that important? Well, it turns out that depending on what model you have, the statistics of these fluctuations are immediately impacted. So there's a one-to-one connection between these two things. So the main idea is these galaxies trace this, and this is tracing the physics itself. And so one analogous thing to think about, yeah, go ahead.
Could you redefine what is the y-axis?
This is just the overdensity. This is like, so this is the mean energy in the universe. There are regions that have more energy, less energy than the mean, and so on. So these are like fluctuations above some mean value in the universe. So perhaps an analogous way to think about this connection here, which maybe is non-trivial. This might also be non-trivial, but it's the one analogy we have, so I'll go with it. And if it's helpful, great. If it's not, that's okay. Don't worry about it. So in the particle physics case, this is a cross-section from the Large Hadron Collider. You put in, let's say, a proton. There's a proton going into this page. There's a proton coming out. They collide. There's a bunch of stuff that comes out of that collision. So let's focus on maybe the red tracks, which are these high energy particles here. My protons have a given momentum and a given energy to them. And knowing those two states, there's some distribution of output particles that I can get from it. So in some sense, I can predict the likelihood that I'm going to get these kinds of configurations from my particle collider. And this is precisely what particle physicists do at colliders. They measure these interactions and they see how well it lines up with the actual theoretical models they predicted. So in cosmology, there's this analogous case in the early universe, where this is kind of a particle diagram. You read this from the bottom to the top. There's some interaction that goes on. There's some inflationary field. Maybe it's interacting with some other particle. It could do whatever it wants. You don't have to worry about the specifics. But the main idea is it's having some interaction, and that determines the correlations it will have at later time. The same way that I put into protons, I prepared a specific state, and that determined what distribution of outputs I was going to get. In this case, that distribution of outputs is our initial density field, and the particle physics that you see determines what correlations you might find in that state. So that's the main analogy you can think about. But again, if this seems a little confusing to you, it's fine. This is a fairly confusing thing anyway. It's not very easy to build analogies here. But the main point is these fluctuations have some strong sensitivity to the particle physics that happens in the early universe. That's the main thing that you need to take away from this. So, okay, we have this connection that we've made here. And so in structure, this is, for example, a slice from a simulation of dark matter in our universe. Structure itself is very rich and very diverse. And so you see things like filaments, you see voids, big, deep, empty regions of space. You see nodes and galaxy clusters that live in that node. And so there are many different ways that structure manifests and different ways that you can measure the structure in our universe. And so just to give you a sampling of some things, gravitational lensing is one way, which I'll talk about very briefly. Dwarf galaxies are a very powerful way that we're going to use more and more. This is from some data that we took from at U Chicago. Galaxy clusters are one of the most massive structures in our universe, so they are particularly sensitive to these kinds of signatures. I'll say a little bit more about that down the line, but this is one thing to keep in mind. And then I'll briefly talk at the end about looking not just at the matter distribution, but at the gas as well. So for example, using the Sunyaev-Zel'dovich emission, which traces the gas pressure. So the kinds of things that SPT, for example, here often thinks about. So let me start by telling you what we have currently to understand something about the early universe. The primary thing, unsurprisingly, is this cosmic microwave background. It's the earliest light that is emitted by the universe, and so it gives you a good sense for what this initial state actually looked like. So we've learned a tremendous amount of things using this cosmic microwave background. One of the theory fellows at Chicago often jokes about how hard it is to be a theorist these days, because you'll spend a month building a theory and then find out that the Planck people who did the best CMB measurements so far have, well, I shouldn't say that the best CMB measurements, with SPT, the best CMB measurements so far, have not only disproved your model, but written a section with 20 different ways they tried to prove it and then didn't find a smidge of a hint or something like that. So it's very challenging to actually build anything for the early universe, given how pristine and how rich this data is. It constrains a tremendous amount about what might be happening in the early universe. One of the other methods that we have that's growing actively these days is looking at the positions of galaxies. I say big here just to distinguish it from dwarf galaxies, for example. These are like Milky Way or group scale objects. And so using those positions, like we talked about before, they trace this initial fluctuation field in the universe. And so you're able to learn something about what this initial state was by measuring the fluctuations in these galaxies themselves. So the main point, these are great, the CMB is great, these are great, but the main concern I have is that 2 probes are really not enough if you want to do something very complete and a lot more robust. So to do this, I want to take an example that's actually from a kind of left field spot. This is a plot regarding early dark energy or evolving dark energy. If you don't know about this, it's perfectly fine. The arguments I'm making are very philosophical, but if you know about this, it's helpful to have this plot on. That's the main point. So there's this component in the universe called dark energy. We think its properties might be evolving with time, specifically its equation of state, its pressure over its energy, we think is evolving with time. There's some hints for this, and a lot of us are spending a lot of time trying to understand whether this is actually real and what that might be. So this plot is from the Dark Energy Spectroscopic Instrument collaboration, DESI, and they have a bunch of galaxies they use to make measurements of this. I would start by focusing on the green contour here. So these crosshairs, if a contour overlaps with these crosshairs, it means there is no evolution at all. So anytime you're away from that, it's a sign that there is some evolution in dark energy. So this green contour is the combination of galaxies with Planck, the CMB, and with supernovae from DES year 5. And so you find that there's some preference to be shifting away from this constant dark energy model. So you can then say, well, this is a combination of 3 things. Sure, it's more constraining. Maybe one of them is weird, and then the model has to compensate in order to make up for that weirdness. So what can you do? You have other data you can utilize. So let's say, you know what, I'm going to drop the CMB, and I'm going to use just data from galaxies alone. So this orange contour is just DES and just DESI, no supernovae. So you still see some difference maybe. You could say the supernovae is odd, and so drop the supernovae and have just DESI and just CMB alone. You still see a difference. I'm not here to make any statements about how realistic it is, but I am here to make a statement about how useful it is to be able to do these kinds of swapping out of different data sets. We're always going to be in a regime where we find something at about 2 sigma, at about 3 sigma, because we're always barely pushing on to the next level. We're not dramatically changing from 1 sigma to 10 sigma precision overnight. So we're always going to be in this situation. And so having multiple ways of accessing information is extremely important when we're getting to actually discovering something new about our universe. And so in this regard, having just 2 probes is very much not enough. If I were to measure something about the early universe with just the CMB and just the galaxies, and those 2 disagreed, well, what do I do from there? Sociologically, everybody would believe the CMB and say there's something wrong with the galaxies, which is fair, but we wouldn't be able to do anything like this kind. And so that's really what is one of the motivating factors for the program that I have. I'm not really saying anything novel. This is nothing that suddenly has come up as a grand idea from God or something like that. People smarter than me have thought about this before. So how do we actually add more probes? Why have we not done this before? And it turns out that the theoretical framework that we have available is the primary reason. The limitations in this framework are the primary reason we haven't been able to do this before. So to highlight this, let me start by showing you the range of scales that different measurements probe, range of physical scales that different measurements probe. So in gray, I'm going to show you the 2 things we talked about before, the standard probes of FNL. The top one has in configuration space and just regular radius, and then wave number a lot. Wave number will show up quite a bit. I apologize. I know not everybody's familiar. I'll try and show radius whenever I can on these plots. The main point is for weak lensing, again, I haven't defined quite yet. For now, you can just think of it as a range, a type of measurement for structure in general, one way of tracing structure. I'll define it a little bit more down the line. But the main point is that weak lensing is probing much different scales than what you do with these 2 existing probes. And importantly, it's probing something that we refer to often as nonlinear scales. So what does that mean? When you're thinking about these perturbations, there are 2 regimes that you can be. These fluctuations in the matter field and the density field, however you define it, can be small enough that you can simply write it as a perturbative theory. You can say I have 1 plus some very small number, and I write a perturbative theory on that. It's very accurate. This is nothing more profound than saying if delta is small, then delta square is basically 0, so I can ignore it. But we often live in a regime, especially on these scales, where things are non-perturbative. These are the scales where galaxies live. A galaxy is not a perturbative fluctuation. It's a whole collapsed object itself. And so you're dealing with these non-perturbative regimes, which means the methods that you utilize have to be different. So that's really where we've been lacking in the current. These nonlinear scales cannot admit just simple perturbative analyses. And for these inflationary models in general, a lot of the community are people that utilize purely analytic methodology. So they've naturally limited themselves to just these existing probes alone. So the tool we have actually is the simulation that I showed you before. A simulation resolves the entire nonlinear structure because it takes some initial state and then it resolves the gravitational equations in a purely numerical sense. It's not making any assumptions about how big or small are the fluctuations. It can resolve everything perfectly. So you get halos, you get collapsed structures, you get merging between them, and so forth. And so it does have everything that we really need in this regard. Okay. So how do you use simulations? Depending on, people have various approaches to how comfortable they are with using simulations. The argument that I want to make is regardless of where you live on this, you will need simulations on some level. So you could either say I have a theoretical model that I believe in, but some of those parameters let me tune a little bit so that I make it more accurate. We often refer to those as semi-analytic models. You can just measure the quantity you're interested in directly in the simulation itself and then build an emulator from it, a non-analytic methodology that just uses the simulation alone. Or you can use these simulation-based methods that I'm not really going to talk about at all in detail. But you can also say, well, you know what? I really trust my analytic theory. I can control it quite well. So let me just utilize that. But even in that case, you still need to know to what extent, to what scale you can trust your analytic theory. And so you need simulations for that as well. So you really can't get away from this fact that you require some numerical simulation of these kinds of models in order to do any analysis on these data sets. And so we need simulations that have these early universe physics in them. So I'll talk about a little bit of jargony things, so I want to define things in detail right now, just so that the nomenclature at least is not too opaque to you all. We often categorize these signatures in the early universe into these three categories. These signatures are nominally correlations between different points in space. So they're correlations between 3 points in space. That's the characteristic way we call them. If you're familiar with the nomenclature of Bauer spectrum and bispectrum, this is often referred to as a bispectrum. But the main point is there are different categories that you can put a signal into. So all of these different models that I mentioned before, they all sort of map, though not neatly, onto these various categories. And so I'll briefly mention this a little bit down the line. And so depending on what category you're in, the way your density field looks can actually be significantly different. I've amplified things a little bit here, but the main idea is if I live in a vanilla universe that has no complicated interactions, I look a certain way, these are all density fluctuations on a 2D slice. And then I start adding some signatures, and now things just visually look quite different to you. This is to say that depending on the signature that you're putting in, what we talked about before, the statistics of the density field can look significantly different. So all I'm saying is we change something about the early physics, then this density field looks significantly different. So depending on which signature you're looking at, things will look different. Okay, so the question then, I'm going to scare you with some equations after this, but it'll be quick, I promise. But the question is, I have this simulation. I need the simulation to include the physics I'm interested in, which means I need the simulation to know something about these correlations between 3 points in space. So how do I end up doing that? It turns out there's this equation. I'm not going to go into too much detail. I just want to explain, to give you a quick taste for why this hasn't been done before and why we're able to do this now. So you want to set up some field. This phi is like a potential. It can be a matter density field. You can treat it as such if you want. So you have this field that has the signatures that you're interested in. So you start with a field that's a vanilla field with no complicated physics at all. And you have an amplitude of this signature, this interesting thing that you're looking for. This function S characterizes what these correlations look like, what the momentum or the spatial correlations of the signature is. So it's a function of spatial modes, but you can forget that. It's just a function that characterizes what this particle physics is like. And then this thing here is really why we haven't been able to do this before. So this integral, even if you forget the physical meaning of this, just think about it mathematically. This is a 6-dimensional integral, which already should be giving you a sense of, oh, what might be the challenge here. Even for very small grids, it scales very poorly. And so 10 to the 20 floating point calculations, if you don't have a sense for how big that is. I'm in Chicago, I'm not that far from Argonne. This is their fastest, not their fastest anymore. Argonne changes fastest GPU clusters every 2 years. But this was their fastest GPU cluster when I was giving the talk first. It's called Aurora, and if I had the entire cluster to myself, this would still take me about 3 to 4 minutes to actually calculate. That is technically feasible, but I think I'm putting a lot of emphasis on Argonne giving me the entire computing time for 3 minutes being feasible. And so this is why we haven't really been able to do this as easily before, because there is this fundamental challenge in performing this integral. And so how do we end up solving that? There's a lot of techniques that show up in both math, especially in the CMB community, where instead of integrating over this function itself, you try to separate it into individual terms. So instead of a function of A, B, and C, you say a function of A times a function of B times a function of C, for example. So this is called factorizing or separating the function. If you're able to do that, then the main thing is these integrals separate, and then you have a much faster algorithm. And so I could have started it at the beginning of my talk, and it would actually be done by the time that I'm here now. It'd be like 20 minutes, 25 minutes. And so that is really the phase that we want to be going into. So, okay, this is not anything that's like novel. This is cut off. Maybe you can see it a bit. This is from 2012. So we've known this for about 10, 15 years at this point. So I'm not, again, saying anything novel. So why have we not actually done this just yet? It turns out for these simple types that I talked about before, the expressions are actually easily separable. They're already separable as they're written down. There's nothing that I need to do here. Okay, so now I'm going to scare you a little bit. This is some of the equations that you actually have to resolve. I don't think it's acceptable to show 7 lines of equation in a talk ever. I only do it to highlight why this has been quite a bit of a challenge. So this is actually, in a sense, an elegant equation. I won't explain this right now. I'm happy to talk about it later. The where it comes from is actually quite elegant. But you're still left with the fact that there are like 7 lines of equations that you have to factorize into this kind of form. So you're not going to be able to do that. Just manifestly, it's not possible to do that. What you can do instead is say, let me approximate this by a sum of things that are each individually factorizable. For those of you who are adjacent to SPT or the CMB community, this is often referred to as a modal estimator. And so this is the same kind of logic that shows up here. Let me approximate my function in some convenient basis that has some factorizability properties to it. Okay, so I'll show you some functions now. So I'll just define what I'm doing here. For each of these different types, there's some 3-point correlation. There's this S function that we write down. It's a three-dimensional function, so let me just plot specific limits of it. That's what the colored lines are. Doesn't quite matter what the colored lines exactly mean. I'm going to contrast those to the black lines, which are our approximation. So we're just trying to look for differences between the colored line and the black line here. So these are three different types. And then now we're able to do it for a much larger set of models. These are now, again, looking at inflationary models where there's some complicated particle physics happening in the early universe. It could be new particles, it could be new spins, whatever have you. It's anything that's different from the vanilla case. And so in each case, you see, once again, these colored lines that are the true model, and then you see the black lines that are the approximation. And it actually agrees to about percent level. There's some that are broader, but I can talk about them later. Those we expect to be worse for various reasons. So we're able to do percent level accuracy. This is a number of different models. One of the things that makes this quite challenging, and so I'm presenting this as if we get the answer, but this took me about 3 years of my PhD. And one of the reasons it's quite challenging is because when you're running simulations, it's very, very easy to put in a tiny artifact that's, let's say, 0.1%, 0.01% of your field. And then that will actually magnify because of gravitational evolution and collapse and so on into quite a large signal at late times. And so you could just say, I induce an artifact for model A and a different artifact for model B. And look, they're clearly different in my late time. So I must be distinguishing things tremendously. But it's really just artifacts in that level. And so there's a lot of numerical techniques that you can pull off. And now we're at the period where the artifacts are not 1%, but rather 10 to the minus 5%. So at this point, you don't worry about it at all. There's literally nothing on the artifact side that can impact your simulation. So you can really trust what you're going to see in the analysis. And so we have over 100 different models. This is just one page of these. There's about 2 others, some of which have Peter's models that I mentioned. And previously, we only had about 5. We had those 5 because they could easily be separated just by the way they were written down. So it's easy to work with. But now we can just do it for any specific model. In my case, I really just went to the CMB community papers and I looked through every model they had tried and then tried to put in my case, how well I could do that. And about 100 of them, to be honest, 100 is limited by how much computing they give a grad student at UChicago. If I had more, I would be able to do much more as well, but we're able to do orders of magnitude better than what we were able to do previously because we have this new methodology for simulating different universes. So I want to highlight this specific panel as well because this was actually that semi-line equation. And you see the colored lines are approximated quite well by the black curves here. And so even though you're starting with something complicated, it's very easy to actually approximate it once you've chosen a right kind of mathematical basis. So it works remarkably well. Yeah, Grant?
I was just wondering, it's kind of a broader question, but is there a benefit to working in like Fourier space here versus like configuration space? Is it just like the math is easier or computationally more efficient or something?
The math is easier. So a lot of for the things I'm talking about here, there are concrete predictions, so you can utilize those. If you're asking for concrete predictions in configuration space, the formalism just isn't available. People will start from Fourier space and then convert it to configuration space to give you anything. But the Fourier space quantity is the fundamental piece that's relevant here. And to your point, it's because a lot of the math here is concerned with momentum, it's concerned with derivatives, and so Fourier space is the natural analogous quantity that you want to use here. Yeah, there's an active, you can ask Peter about this, you might know better, there's an active effort in the community to think about the configuration space predictions for this, but there isn't any concrete work that's actually happened on it. There's more kind of ideas of what one might do. Yeah. Yeah, go there.
I mean, there weren't really 100 different theories in the sense of a whole bunch of those things had similar physics. They were grouped in some way.
Yeah.
Ways to just use this to like get rid of entire classes of them.
Yeah. So 100 models, as you point out, I'm using the same differentiation that the CMU community will use for different models, where different enough particle masses are considered different models. You can totally get rid of you can get rid of classes in the sense of similar to like the dark matter case, where you can't quite completely get rid of a model, but you can get the interaction, saying how likely is it that this is the strength of the coupling for a dark matter particle and so on. You can get it down to a low enough level that you no longer think it's a viable candidate, or more importantly, it has to be very fine-tuned in order to be the real universe. So it's a very similar picture here. I'll show you one plot maybe very soon that is much more analogous to the dark matter case, so you can think about that in very similar terms. Yeah. Oh yeah, go ahead.
In some of the plots, the black curves do seem to have like a lot of weight.
Yeah. So this is, let me point to these two here specifically. I think these are the worst ones. At the end of the day, I glossed over this because this would have been too technical, but I'll briefly mention this at least, and I'm happy to chat about it after. It turns out that you can write down these very nice theories and mathematical arguments that I talked about before, but they translate very poorly to a computer. because a computer has very finite precision for how it can compute numbers. And so on some level, you're going to get issues because of the fact that there is a finite precision for numbers. These things here, the way you get around this precision problem is by limiting the bases in specific ways. You do not utilize all the modes that are available to you in that basis function, but you utilize a subset of them that you think are adequate enough to actually represent the problem. For these models, the subset that worked really well for these just happened to have all much large, don't seem to capture the actual model as well. I will also say that this plot alone is not quite a useful metric on how well a model is being captured, because this is formally a three-dimensional function, and I'm showing you 3 lines in that three-dimensional space. And so you can, it's kind of confusing how you define what is a good approximation. Right now, I'm saying it as these 3 different limits need to be approximated to 1%. You could also say, well, the bulk of the function should actually be approximated well. And so for all of these, the bulk is still approximated well to like 99%. And so that's a bit of a ambiguous question, to be honest, not question, but ambiguous answer, because the way we define agreement between the approximation and the model is a little hard. But in this specific case, it's because of this basis decomposition. Thank you. Okay, we move on. Okay, so we can approximate that. I have a bunch of simulations that I have run to do exactly this. This is called the Oligum suite. I name things after a number of Tamil words. This means world or universe. And so there's a number of simulations that are meant to tell you something about the observations that a survey would make on the sky. So it's not 3D snapshots in X, Y, and Z, but rather RA decks on the sky with redshift and so on. Okay. And so we have these simulations. It's something I produced over my PhD, and so I want to utilize this to study something about primordial physics. The first point I want to make is that when you introduce these PNGs, there is a distinct response that structure has on them. There are about 2 things that happen. First is galaxy clusters. Their formation is altered. I'll show you a cartoon to induce this a little bit better. One thing that's quite interesting is that dwarf galaxies actually go the other way. So if your model causes you to have way too many clusters, or way more clusters than usual, what that means is a lot of the matter in the universe is locked up in these massive clusters. There's a lot less matter that is now available to form smaller galaxies because so much of it is locked up in these big objects. So as a result, these smaller objects form a lot less. There's just not matter, and there's not enough matter available. So this really comes from the point that there's a fixed amount of matter in the universe, and so all of that goes into bigger objects. There's less available for small objects. So this is quite neat. The rest of the universe remains unchanged. So if I look at fluctuations on large scales and so on, all of that looks similar to a vanilla cosmology universe. So in the galaxy cluster case, one way to think about it is looking at distributions. So this is the distribution of densities in the early universe in a simple case with no complicated physics to it. And then this one is just a mock where I have some complicated particle physics pattern, and then it shifts the distribution and causes a skewness to it, for example. Just go ahead.
Kind of general about what changes you've made to the primordial physics, and like for what class of theories do you get the result that galaxy clusters are bigger or form earlier or more dense and then dwarf galaxies are reduced?
Okay, good. This actually goes directly to this plot, so let me do this. I wasn't going to mention this before, so thanks for asking the question. All of these classes of theories induce some kind of skewness in the distribution. They take something that is asymmetric and then they tilt it in some fashion. So you have a tail that goes to either much lower densities or much higher densities. You could go either way. It depends.
Generically non-Gaussian initial conditions.
Just non-Gaussian initial conditions. Yeah. So this is why we call it non-Gaussian, because you've taken a Gaussian distribution, you've tilted it in some way, for example. And so galaxy clusters form from the peak of the density distribution, from the regions that are extremely overdense, that are very rare. And so let's say these regions are what form galaxy clusters. In the vanilla universe, there's some space under this PDF, so I can utilize that. In this version, there's so much probability that I've shifted away, there's barely any left to actually form clusters. This initial field has very low peaks and has a lot more underdensities, for example. And so I would get very few clusters in this case and a lot in this case. And so this is a generic prediction you would get from any kind of primordial non-Gaussianity, because all of them are going to tilt the distribution in various ways. So they will always change galaxy cluster abundances. Once you do that, they will change the dwarf galaxy abundances as well. I think you were first, Brian.
Voids.
Exactly. Perfect. And the cosmic void abundances change dramatically because you get way more underdense regions. Perfect.
Why don't you tilt it that way?
just because I wanted to show one diagram. That's it. So this I don't know where I put this parameter FNL, which controls the amplitude, can be positive or negative. So if you change the sign, then this gets tilted the other way. That's all. It would reverse. You would get more clusters, fewer voids, and so on. So they're all relative to each other. They all have a fixed direction, but the value of FNL still sets the first direction, so to speak. Yeah. Okay, so any and all measurements of structure will probe this physics. In the interest of time, I'm going to quickly skip through the weak lensing piece. So I won't actually do this. Just trust me that there's something called weak lensing that will measure the structure of the universe, and it's a useful way to do it. So all of these overdensities and underdensities will affect the shapes of galaxies, and you can utilize them to measure weak lensing. If you want to know more than that, you can go talk to Aaron after this. You can talk to me also, but Aaron will be here longer than I am. Okay. So, okay, what do we want to do? We want to take our simulation, we want to make mock light cones of the sky, and we want to mock up a survey. Those of you who know anything about DES will recognize the tank-looking footprint. So I'm just mocking up DES in this example. But you want to say, how do I go from a simulation with these non-Gaussian entities and see what it does for the observations I would make in a survey? And so given these observations, you have one choice. You want to go to some constraint on a cosmology parameter. You have a couple of choices you can make. This is a map. It has, let's say, about 2 million to 3 million values in it. You don't want to directly use those. So instead, you summarize them in some way. So one thing that we often do is to look at correlations between 2 points in this map, and so convert these pixels into some statistic that is set by the distance between points. And then you can get cosmology from that, and everything works great. You can do the same exercise, but use distances between 3 points or 4 points, or you can go forward and just say, I'm just going to give everything to a CNN, and it's going to figure out what's the best compression. You can do any variety of these. I'm going to look at the very simple versions here, but I'll note that these methods can give you maybe 50%, 60% improvement over that. I guess we'll be exploring these quite extensively in desk, so you can ask Gautam later. He will also be here longer than I am. Okay, so this is the main plot I wanted to get to, which is what do we think the constraining power for this can be using just weak lensing alone? The way to read this is if you've seen a dark matter constraint plot, it's kind of similar to that, only this is not constraints, it's forecast, so it's telling you what weak lensing could potentially do. This parameter here is the amplitude, so you can think of it as like an interaction strength. Any model that predicts something above a given line is ruled out. This is a model as a function of some parameter of the particle you're interested in. So in this case, it's mass and some appropriate units. The different lines are slightly different interactions that a particle go through. That doesn't quite matter. Just focus on whichever of these lines you like best, and you can pick that. For comparison, you want to utilize the cosmic microwave background. What constraints do we have from that right now, which is what we show in the gray? So order of magnitude, you're about a factor of 2 between what the CMB does and what you're going to be able to do using weak lensing in the near term. And this is for one generic set of models. But remember before, I said weak lensing is great at probing smaller scales. Let's go ahead.
CMB primaries?
CMB primaries, yeah.
Okay.
We don't think CMB lensing will actually add too much to this. I won't go into that much detail. I'm happy to answer that later. It has to do with how much it's integrated along the line of sight. So this is just the CMB primaries in this case, just temperature and polarization. Okay. So this is a model where the signal is actually imprinted on smaller scale. So as you go to the right in wave number, higher wave number is smaller scale. And you find that, once again, the LSST, the lensing line, will actually perform better than what the CMB does. And this is sort of expected because as you imprint features on smaller scales, you're pushing that feature out of the regime that the CMB is very good at probing. And so you're putting something in a regime that weak lensing will outperform the CMB, and you necessarily see that here as well. So there's a variety of different things. As I mentioned, there's 100 models, so there's 100 different plots that I could show you. But the main takeaway is we have these 2 probes. We looked at one extra probe for the first time, and immediately we saw constraining power that was actually comparable to the CMB. And I mentioned there's like many other probes that we utilize to study dark matter, study dark energy. And the very first one already is showing a lot of promise. And so what can we do beyond that, actually? This methodology that I've made for these initial conditions is available. I just wanted to put this because another Thummer word. Autumn means beginning, so it's a pretty good name for an initial conditions generator for the universe. This is useful. I only mention this because a number of people who work on simulations is a very easy spot to plug into. It plugs into any simulation pipeline that you already have. It's a very easy way to decouple the problem, so to speak. Okay, I'm going to very quickly go over this multi-wavelength side just to get to one plot because I'm running lower on time. Because everybody has very nice questions. Thank you. The main point I made at the start was once you have these simulations, you want to also be able to fold in multi-wavelength data, not just a single wavelength alone, not just the optical on its own. So what can you utilize there? This goes to the question of how do you model astrophysics in these kinds of formalism? So far, everything I've talked to you about, I've just said matter and I've said gravity. I haven't said anything about baryons, about hydrodynamics, about just astrophysics in general, right? And so you can start by saying, what is the right thing to do? If I wanted to constrain some parameter, so let's say this was FNL, given some data, then there are certain things I don't know about galaxy formation. And so what the right thing to do is to say, I have some uncertainties and I'm going to marginalize over this. This is just a marginalization integral. This turns out to be a bit of a challenge because normally, what do you say is the prior for these parameters? What is the range of uncertainties that I have? One way people quantify this is using simulations of baryons, these hydrodynamical simulations as we call them. I spent a very significant amount of life showing the various different ways that those might not agree with each other. Depending on which simulation, which observable you look at, there's varying levels of difference. It's somewhat expected because each sim is actually solving a slightly different set of differential equations. You're not expected to agree. I'm not going to go into that in too much detail either in the interest of time. I apologize. But the main point I want to make is this is not really what you want to do. You want to marginalize over parameters, but you also want to marginalize over models. I have various models for what AGN feedback might do on parsec scales. I cannot fix to a specific model and just vary a parameter. I have to marginalize over the models themselves. And so that is the precise thing I need to do, but it's sort of undefined in a sense. Because what are the space of models that are complete that I should marginalize over? There's a certain set of things that sociologically we have decided because some people have discovered them and we found them appealing, so we looked at them. But there's a number of other models that we could utilize as well. There's just an ill-defined question to define the space of models. And so some of the things we've been working on actively is to not rely on just the kind of microphysical processes of what is going on, but instead specifically look at them only at the observable level. So we're going to define how astrophysics behaves using just profiles of different components like stars and gas and so on. Those are all things you can directly observe. And so those are things you can constrain with the data directly rather than having to assume anything about model or specifically about what microphysical processes are going on in our universe. So the main way this works is you have an n-body simulation with primordial non-Gaussianities or whatever have you. And then you add some perturbation to it in order to get some baryonified version. So baryonified in the sense meaning that includes the effect of astrophysics at large. That can be a variety of different things depending on how you define the problem. The main way this works is, again, you define some set of perturbations depending on what kind of physics you want to include. So if I've said my AGN was really energetic and blowing stuff out, then maybe I need to go to my simulation. This is a halo center, let's say, and then I perturb the particles outwards to mimic the impact of AGN blowing things out relative to a dark matter only simulation. And vice versa, you can do the opposite if your universe is dominated by gas cooling, but we know that's not the case. This is just for illustrative purposes. This is a methodology that's existed for about 10 years at this point. It goes often under the name of baryonification, though it's not in the title, apologies. But this has now been used on a variety of different data sets as well. And so this is actually a subset. There's about 12 different papers at this point. It really picked up speed in 2025. And so there's a lot of different utility we've taken from these kinds of approaches that only rely on profiles alone. Sorry, I didn't realize it was getting cut off that much, but you can infer probably what this says. It's just 10 to the 1. So you start with some assumption about what matter distributions look like in a simulation with just dark matter, no baryons at all. We know what that is like. And then you make some assumptions for what the gas and the stars and other components look like. And using those two things alone, which are, again, profiles, so they're things that you can actually constrain on data. And using those two things alone, you can define these functions that I talked about before. So if your gas profile for some reason did tell you that the gas was incredibly cold and there was nothing on the outskirts, nothing was being blown out, then the model would tell you this is what you need to be doing to your n-body sim to mimic that effect of astrophysics. So what is the main takeaway? Using this, you can now define things like pressure profiles, so something like a Sunyaev-Zeldovich effect profile you would see in SPT, because all you need is to know what the total matter is like, you need to know what the gas density is, and you make some simplified assumption to get what the pressure of the gas is like. Once you have the pressure, you can also get the X-rays as well. I'll go a little fast on this, apologies, but this is just telling you that we can get all the quantities, thermodynamic quantities we need in order to predict different things about the universe. I have to go very fast, apparently. Okay, so we can take these different models and we can apply them to different simulations, and we can get these different fields that are of interest to us. I've applied this to a different pipeline. This is not a Tamil word. I apologize if you thought this was a Tamil word. This is just a generic English one. And you can apply this to a variety of different probes. Actually, can I just plug this in so I don't actually cut out?
There is a outlet to your right on the wall.
On constant, I can get done. Okay, thank you. This is because you didn't help me set up the Zoom, by the way. Okay, as long as we're in agreement. Okay, I teased him too much. I shouldn't do this. I apologize. Okay, so this plot is just showing you that you can actually make observations of different parts of this. Oh,
We're out of place. Can I have that one?
yeah, you can have that one.
You just stand there and put it forward for you.
You, no. That one is
Oh, that one.
my U Chicago security list.
Okay, cool.
Don't ask about U Chicago computing security.
Okay.
Right. No, you're good. You're good. You're good. Okay, so you can make different observables of the sky. This is just showing you we can now make maps at the SE of the weak lensing and the X-ray counts. Doesn't matter too much. It's also not the prettiest plot because it's very noisy, so you can't actually glean too much. But the main point I wanted to get to is this, which is, let's say previously I showed you just constraints from weak lensing. What if I can add TSE? What if I can add X-ray? What can I do? So the green contour versus the blue is what you want to look at. And it turns out there's significant constraining power you gain in FNL, this parameter, once you start adding this multi-wavelength data. Things that we have, surveys that are already online are going to be coming up online, can significantly constrain this. Why? Because the TSE and the X-rays are emission. These fields have emission that is dominated by clusters. The abundance of clusters we just talked about is affected by these primordial non-Gaussianities. So the emission in these fields is also affected by primordial non-Gaussianities. And so you're able to get a significant constraint on this, a factor of 2 improvement, because you're utilizing multi-wavelength data as well. The other parameters here is just omega matter, the fraction of matter in the universe, some set of fluctuations, and then this is a feedback parameter that I'm not going to explain at all. But the main point is multi-wavelength science is really helping you out in doing this kind of analysis, and we're now at the stage of doing this. Yeah, Gil?
So is it the massive clusters that help or the less massive ones?
It is primarily the most massive ones. The further along you are in the tail, it helps a lot.
So do you actually need future SE or could you just use the blank catalog?
I think in practice, the way it ends up working is there are 2 effects here. One of them is, as you mentioned, big clusters, abundance is changing, gives you FNL. But there is a significant benefit from the baryon side of having the TSE. And for that, I think you do want to go to lower masses where weak lensing will be affected, like group scales, like closer to Milky Way scales, and so on. So I think for the FNL side alone, maybe Planck would be adequate on its own. I don't know. It kind of depends on how well you think we can get rid of the foregrounds, which I think would be the limitation. But for the baryon piece, I think going to smaller scales and that would be helpful. I don't think Planck alone would be adequate in that scale. Yeah. Okay. All right, so what are we going to be able to do with primordial physics in the current gen? I can say current gen because these surveys are now here and online. It's not really next generation. It is data that surveys that we have right now. Yeah, got it.
Sorry, just before you also. So
Yeah, go
you've
ahead.
done all of this work on baryonification for
Yeah.
the sims.
Yeah.
You've gotten these multi-wavelength sims to test with all of the different observatories.
Yeah.
For these different surveys.
Yeah.
But are you never going to use the fact that some of this multi-wavelength data can be taken for the same systems? So LSST
Right.
and Simons
Yeah.
are both in the sub. They are both giving you data on the same system.
So on the same systems, okay, good. Right now, the way I would think about this is using the fact that there's overlap between surveys. The way I would think about it is it's averaging these multi-system observations across a wide statistical catalog. You could totally go in and say, I'm going to, for example, make a catalog of clusters in the X-ray and the SE and the optical. I think for this specific analysis, thinking about the correlations that you have to include is maybe a little more non-trivial. But a simulation-based analysis of the kind I'm suggesting here would be one of the ideal ways to do that. So I think that's definitely viable. One of the places where I think this kind of approach is even more useful is the kinematic SE effect, where you often can only make, at least in the simulation sense, observations of individual systems rather than like large-scale correlations. And so there, I think this is what the thing you suggest is going to be the viable approach. Yeah. Okay. Good. So the main thing towards the end now is I mentioned before this one probe, which I didn't explain. I apologize. You're still gonna have to trust me. I mentioned weak lensing so far, but there's a variety of different things that you could utilize. And so again, just to orient you, these are the radius scales on the top. So everything that is colored is going from radius of 10 megaparsecs down or from K of 0.3 and above, for example. So the probes in gray are the things that we've utilized for cosmology. So dark energy, dark matter, and so on. And for FNL, these primordial science cases. These ones here, we've not used for FNL. None of these were really actively used for FNL. There's maybe one paper on the cluster counts that came out that SPT did a while ago and that acted quite recently, but otherwise there's really nothing that's quite happened. But these are all established probes of cosmology. And what I mean by that is we've made these measurements, we've used them to study dark matter or study dark energy. We know how to work with them, we know what their limitations are. So I'm not suggesting anything novel in that side. I'm suggesting we take these approaches, these measurements that we already have, and actually translate those into studying something about the primordial universe. It's a much smaller step than one might imagine in the way that I'm presenting. And so the opportunity is quite large. So these signals, again, as I mentioned, they're nonlinear, so that's why you're not able to utilize them. But the factor improvement you get is about a factor of 1,000 in the range of scales that you can utilize. So in all of these models I told you, you could totally come up to me and say, I'm a theorist, and I know with 99% certainty, there is a feature at this K of 10 scale. So I could make a measurement that might probe that. Nobody currently has an inference pipeline that could constrain that feature and tell you how likely it is that it exists or doesn't exist in the data. So it's precisely the kind of question framing that I think we should be able to actually answer, given all the things that we've done as a community to utilize these kinds of measurements of the sky. And so that's precisely what I'm trying to work towards, and it requires all these simulations, it requires these multi-wavelength approaches. And so that's why I've spent 5 years of my life on this, because of these kinds of questions. So at the end, you could say that it will help a lot with consistency. You have more probes, there's more consistency or more redundancy that you can utilize. And even if you don't think that is viable or that's as interesting, you will just trust the CMB, which is fine. I understand why. There's a lot of opportunity for these scale-dependent studies of the kind I just mentioned here. Even if you don't see a signature, even if your dwarf galaxy counts are like very, very uncertain, the fact that they're at a scale that's about a factor of 100 away from the CMB means you have a very long lever arm, as we would call it. You can understand the scale dependence quite well, and you can constrain it quite precisely. There's a lot of opportunities for studying these other physics that we simply have not been able to test because we've been limited in the kinds of modeling approaches that we have. Okay, so the last thing I want to do, because I am here, I know a little more over time, so I'll take 2 more minutes. There's a lot of synergy with upcoming data. For all the probes that I've mentioned here so far, the optical surveys are going to be critical. Even for the SC, there's a lot of calibration that you can do with optical surveys, so it'll be very important. And we're obviously going to do a lot of this with LSST, but in the meantime, so this is a plot of where we'll get to in 10 years. The first data release will probably be another 2 or 3 years from now. I don't know. I guess we'll find out. Gautam gave a thumbs up, or a thumbs down. I didn't quite catch which direction that was going. But the things that we want to utilize, and I want to say this since I'm at UIUC, is we have a lot of data from the existing generation of surveys, from the dark energy survey in particular, this tank-like footprint, which had a ton of processing here at NCSA in particular, with a lot of UIUC colleagues who really led the charge on getting this data. But more importantly, there's this companion survey called Decade that we've been building out of UChicago. It's an effort between UChicago and NCSA in particular. And the idea is to take a lot of data that we have here that's kind of archival. It wasn't meant for surveys. It was taken for white dwarfs, nearby galaxies, star formation rates, and so on, and utilize them to actually do a coherent survey of the sky. So it really means a lot of reprocessing of this data. And so having more area is very important for this primordial science because you're studying very massive objects. And so it's useful to look at wider area than it is to look at very deep, very faint galaxies instead. You know these are bright and very large objects in the sky. This I'm going to skip over, but the main point, I actually don't want to make this point either. There's a bunch of people that were leading this, I did a bunch of stuff, blah, blah, blah. But the main point I want to make is actually that all of this was really possible because of NCSA folks, Robert in particular, Robert Grundle, who many of you may know, helped a tremendous amount with this, and Monica as well. There's a number of other folks like Don, like Andrew Manning, a lot of folks at NCSA that really led the charge on this front. And the survey was called Decade, DCAM All Data Everywhere, and I'm told that name comes from Eric Morganson, who was also an NCSA research scientist a while back. So there's a ton of stuff. A lot of my PhD was actually this, rather than the stuff that I was talking about primordial physics. So I think when I go to my thesis defense, they're going to think I'm going to talk about Decade, but I'm not. Either don't spoil them on that. But I mostly wanted to end with this note because I've benefited a tremendous amount from the infrastructure and the people at NCSA. So given I have this one other chance as a grad student to come here, I just wanted to make that note as well. There's a lot of improvement, blah, blah, blah. I'm not going to say that either. So at the end, I've told you a little bit about this landscape for primordial physics. I've told you that we have a lot of new frameworks that we can utilize to convert this into observables, and how we can convert those simulations into multi-wavelength observations of the sky as well. So what do we do from here? I think going back to this plot, which was the evolving dark energy case with many different data sets being swapped in and swapped out, I think we're very much in the position where we're now going to be able to do this, but rather for the PNG case. We're going to be able to extend this from just 2 probes to 5 or 10 or what have you. And we'll be able to soon make this kind of plot. What we find, I don't know. Whether it'll be interesting, I don't know. But we'll definitely be able to make this plot. And that's as much as I can guarantee at this point. So if you want to know anything more, this QR code takes you to my website, but also Joaquin pronounced my name incorrectly, but you can Google my name. I'm the only one you pronounce it fine. I'm sorry. Keep trying. All right, I'm ripping on you too much. I've only met him in like non-academic settings, so I'm having a little bit of adjustment problems here. But you can just scan this QR code. You'll see all the different papers and works that we've been doing on. But sorry for going a little bit late. Thanks for your time, and happy to take questions.
Questions?
Yeah. Go ahead.
So can you explain how measurements of small scales are going to help you with FNL? I thought FNL, you must need the larger scales.
Yeah, so that depends on normally when somebody tells you that they're measuring FNL, they almost always mean this type that's called FNL local. And that has this unique signature where it impacts the clustering of galaxies on very large scales. So that's what often people say large scales are very useful for FNL. There's a much broader class of signatures you could look at that come from a much broader set of primordial physics. And I showed you a little bit before that they impact the formation of galaxy clusters. And clusters occupy the smaller scales in our universe rather than larger scales. These are like 1 megaparsec objects. And so by going to smaller scales, you're kind of maximizing your signal to noise of how well you understand and see these clusters formation. So you get information from that. That's the main idea. Okay. Yeah.
Okay. Yeah, it was a really great talk. My question is related with like modeling bias. So I think for the theoretical part is the things you have like 100 different models, which
Yeah.
is quite comprehensive. But for the observation part, like for example, in you talk about the bion SAM, right?
Yeah, yeah.
That depends on, if I remember correctly, like calibrate on certain simulation and depends on a few assumptions.
Yeah.
So my question is,
Yeah.
like when you're actually applying to observation,
Yeah.
what's your plan to dealing with this kind of modeling bias?
Yeah, good. So this factor of 2 improvement statement, I didn't go over this in detail because again, for time, but this factor of 2, this triangle plot is just 4 out of a set of maybe 12 parameters on the baryon side. So we think we're doing at least a fairly comprehensive job in calibrating the impact of astrophysics with these flexible baryon SAMs. The fact that we have weak lensing TSE and X-ray allows you to self-calibrate very precisely. We're already doing this in the weak lensing world where you take X-ray observations of galaxy clusters, going back to what Gautam said of multi-wavelength analyses of the same objects, and we use those to constrain what the baryon fractions in objects are like. This is doing a similar analysis, but with way more parameters. So you can always make the criticism that I should be varying even more parameters. I think that's fair. We won't know until we look at the data, I suppose. But at the very least, I'm not varying 1 or 2 parameters. I'm varying about 12 in this case. So I am doing as complete a job as we know right now for how much we should vary the astrophysical impact.
That was a great step.
Yeah. Yeah. Oh, sorry. Go ahead.
Yes, so, well, thanks for your talk. Just to follow up with the question you already
Yeah.
had, so with the, a little bit. So for the FNL, for the kind you're talking about, is there, how low can you go? Like for the local version, there's like a limit you got to hit.
Right.
PR.
Yeah.
Is there anything comparable with what you're talking about?
Not quite. So one of the interesting things about this scenario compared to this FNL local, so just briefly, I know we talked about this, but just briefly for this FNL local type, there's a lot of easy theoretical arguments that you can make to say what is the level you should expect. For a lot of these models, at this point, the simulations are actually ahead of the theoretical capabilities. So there's just not as much of the techniques available to answer these specific kinds of questions. So we often answer them phenomenologically. So a theorist would say, this is a template that I think is feasible, and then we go and measure it. It's a lot harder for them to say, this is a feasible template, and I think this is what the amplitude is going to be. We just don't have the techniques to actually answer that right now. Yeah.
Aaron and Josh. Yeah, like with this plot, seems like you're trying to do like fairly complete marginalization of the possible models.
Yeah.
What about intrinsic alignments?
Good question.
Like what kind of assumptions you have to make, and like, how does that affect like how much better?
Yeah. So I think that's one of the things that's a little bit harder. All the constraints that I showed you are with marginalizing over an NLA model. I'll speak jargony because you know this, and I need to give you an answer. So intrinsic alignments are like the correlations and shapes of galaxies because of tidal fields. And so the NLA model is marginalized over this plot.
Well, like, to what, how small the scales do you go, like, using NLA?
This is a good question. I honestly don't think as a community we have as clean of an answer because we're limited in the simulations we can utilize to study galaxy shapes on gigaparsec scales. So right now, the best you can do with a simulation-based analysis is to just assume this NLA model. It seems to work well in analyses we've done in DES, but I agree with you that that's, I think, one of the main limitations and things I need to think about for this. Yeah.
But sort of following up just a little bit on that,
Yeah.
you know, does it matter if you can't go to very small scales if you know at some point that the prescription itself that you got,
Yeah.
even before baryonification with your Ullagum sims,
Yeah.
is unrealistic? You had said galaxy clusters are
Yeah.
affected, but dwarf galaxies compensate,
Yeah.
and nothing else changes. And a supernova person like me is like, what are you crazy? Like supernova, it's certainly affected.
Right.
And lensing signals are affected.
Right.
So
Yeah.
you know, if the goal is to constrain the space
Yeah.
and rule models out,
Yeah.
what can we do without? Yeah,
What other things can we do is the question,
Yeah,
right?
exactly.
Okay, so in this plot, I didn't talk about, I don't know where it is, but in the plot of different probes that I have, strong lensing is one of them that we're looking at because this affects also this plot here. At least if, I don't know if any of you were on a proposal committee that I submitted to for postdocs, but if you did, there would have been a green bar here that had strong lensing as well. But the strong lensing, I think you can utilize as well because this also will affect the rate of subhalos forming in the universe. And so the strong lensing that people use for like dark matter constraints will also be affected by things like this. This requires slightly different simulations that we need to utilize because you need smaller resolution, much more zoom in versions, for example. But I think things of that kind that you're asking will definitely be affected. When I was saying it was a little flippant for me to say nothing else changes. It's nothing else changes from like a large scale structure person only thinks about correlations and so on. If you go to sufficiently large correlations, things won't change. But for probes that care about things on small scales, things will definitely change for sure, guaranteed. Yeah. So that's what I need to be doing for the next whatever 3-4 years. And I hear people at Stanford know about subhalos, so maybe it's a good choice to go there. Yeah.
Okay, let's think that again and then we can.
We're going to